Example 8-4. Consider the definition of the following class roll dice. Public class roll dice, instance variable int num, default constructor roll die, num is equals to 1. We have a method roll a die, which uses a random number generator to randomly generate a number between 1 and 6 and stores the number in the instance variable num and returns the number. We have next the method getNum, which returns the number on the top face of the die and returns the value of the instance variable num. Next method, we have the toString, which returns the value of the instance variable num as a string. We leave the UML class diagram of the class roll die as an exercise for you. The following program shows how to use the class roll die in a program. Public class test prog roll die. Then we have in line 4 the scanner. This program works as follows. The statements in lines 7 and 8 create the objects die1 and die2. And using the default constructor set both the dice to 1. The statements in lines 9 and 10 output the number of both the dice. The statement in line 11 rolls die1 and outputs the number rolled. Similarly, the statement in line 12 rolls die2 and outputs the number rolled. The statement in line 13 outputs the sum of the numbers rolled by die 1 and die 2. The statement in line 14 again rolls both the dice and outputs the sum of the numbers rolled. Copy constructor. Suppose that you have the following statement. Clock my clock equals new clock 8:45:22. You can use the object my clock to declare and instantiate another clock object. Consider the following statement. Clock a clock equals new clock my clock. This statement declares a clock to be a reference variable of type clock, instantiates the object a clock, and initializes the instance variables of the object a clock using the values of the corresponding instance variables of the object my clock. However, to successfully execute the statement in line 2, you need to include a special constructor called a copy constructor in the class clock. The copy constructor executes when an object is instantiated and initialized using an existing object. The syntax of the heading of the copy constructor is public class name, other objects. For example, the heading of the copy constructor for the class clock is public clock, clock, other clock. The definition of the copy constructor for the class clock is public clock, clock, other clock, hr equals other clock that hr, mean equals other clock that mean, sec equals other clock that sec. If you include this definition of the copy constructor in the class clock, then the statement in line 2 declares a clock to be a reference variable of type clock, instantiates the object a clock, and initializes the instance variables of the object a clock using the value of the instance variables of the object my clock. The definition of the copy constructor of the class clock can also be written as public clock, clock other clock as parameter, set time, other clock.hr, other clock.min, and other clock.sec. The copy constructor is useful and will be included in most of the classes. If you are using versions of Java lower than Java 5.0 or you do not include the preceding import statement, then you call the method pow in, for example, you use the method pow 5, 3. You will call this method as follows: math.pow 5, 3. That is, we can simply call the method using the name of the class and the dot operator. This example, the name of the class is math and the method is pow. We cannot use the same approach within the class clock. Although the methods of the class math are public, They also are defined using the modifier static. For example, the heading of the method POW of the class math is public static double POW, double base double exponent. The modifier static in the heading specifies that the method can be invoked by using the name of the class. Similarly, if a data member of a class is declared using the modifier static, it can be accessed by using the name of the class. The following example clarifies the effect of the modifier static. Consider the following definition of the class illustrate. Public class illustrate with private int class, private static int y, public static int count. Suppose that you have the following declaration. Illustrate object equals new illustrate. The reference variable illustObject can access any public member of the class illustrate. The method increment y is static and public. So the following statement is legal. Illustrate that increment y. Similarly, because the data member count is static and public, the following statement is legal. Illustrate that count plus plus. In essence, public static members of a class can be accessed either by an object, that is, by using a reference variable of the class type, or using the class name and the dot operator. Static variables, data members of a class. Suppose that you have a class, say my class, with data members static and non-static. When you instantiate the objects of type my class, only the non-static data members of the class my class become the data members of each object. What about the memory for the static data members of my class? For each static data member of the class, Java allocates memory space only once. All my class objects refer to the same memory space. In fact, static data members of a class exist even when no object of the class type is instantiated. Moreover, static variables are initialized to their default values. You can access the public static data members outside the class, as explained in the previous discussion. The following example further clarifies how memory space is allocated for static and non-static data members of a class. Suppose that you have the class illustrate as given in example 8-5, then memory space exists for the static data members y and count. Consider the following statements. Illustrate object 1 equals new illustrate with 3. Illustrate object 2 equals new illustrate with 5. The statements in line 1 and 2 declare object 1 and object 2 to be reference variables of type illustrate and instantiate these objects. See figure 8-14. Now consider the following statement. Illustrate that increment y, illustrate that count plus plus. After the statements execute, the objects and static numbers are as shown in figure 8-15. The output of the statement system.out.println illos object 1 is x equals 3, y equals 1, count equals to 1. Similarly, the output of the statement system.out.println illos object 2 is x equals to 5, y equals to 1, count equals to 1. Now consider the statement illustrate count plus plus. After the statement executes, the objects and static members are as shown in figure 8-16. The output of the statements system.out.println illos object 1 and system.out.println illos object 2 is x equals 3, y equals 1, count equals 2, x equals to 5, y equals to 1, count equals to 2. The program in example 8-6 further illustrates how static members of a class work. The program works as follows. Static data members y and count are initialized to 0. The statements in lines 1 and 2 create the illustrate objects illus object 1 and illus object 2. The instance variable x of illus object 1 is initialized to 3. The instance variable x of illus object 2 is initialized to 5. The statement in line 3 uses the name of the class illustrate and the method increment y to increment y. Because count is a public static member of the class illustrate, the statement in line 4 uses the name of the class illustrate to directly access count and increments it by 1. The statements in line 5 and 6 output the data stored in the objects illus object 1 and illus object 2. Note that the value of y for both objects is the same. Similarly, the value of count for both objects is the same. The statement in line 7 is an output statement. The statement in line 8 uses the object illus object 1 and the method increment y to increment y. The statement in line 9 sets the value of the instance variable x of illus object 1 to 8. Lines 10 and 11 output the data stored in the objects illus object 1 and illus object 2. Note that the value of y for both objects is the same. Similarly, the value of count for both objects is the same. Moreover, notice that the statement in line 9 only changes the value of the instance variable x of illus object 1 because x is not a static member of the class illustrate. The statement in line 13 uses the object illus object 2 and the method increment y to increment y. The statement in line 14 sets the value of the instance variable x of illus object 2 to 23. Lines 15 and 16 output data stored in the objects illus object 1 and illus object 2. Notice that the value of y for both objects is the same. Similarly, the value of count for both objects is the same. Note that the statement in line 14 only changes the value of the instance variable x of illus object 2 because x is not a static member of the class illustrate. Note, here are some additional comments on static members of a class. As you have seen in this section, a static method of a class does not need any object to be invoked. It can be called using the name of the class and the dot operator. Therefore, a static method cannot use anything that depends on a calling object. In other words, in the definition of a static method, you cannot use a non-static data member or a non-static method unless there is a locally declared object that accesses the non-static data member or the non-static method.